Hello and welcome back to going over homework. This homework is in AP Physics. This is 4-2, free body exercises, and in STEM Physics, which is basically the same homework, but it is just called free body exercises. And the answer key should be the same in any case. It's the same basic tool, the tool for our toolkit for analyzing force systems. You can see some of these I've already done on this piece of paper as we did them in class. So let's just take a look at number 4. We have a free body diagram of a rock hanging from 2 ropes. And so there's a free force of gravity pulling down, and then we would have a tension in this rope. We can call that tension 1, and perhaps a tension in this rope, and we'll call that tension 2. And these should be equal because the angles are equal. In this problem here, the tensions would be different because the angles are different. And so one of them is going to be tighter than the other, or more taut. All right, for number 6, we have a rock sitting on the ground. So we've got the force of gravity and the normal force. Surface, the perpendicular force that something experiences when it's resting against a surface. All right, so going down here, I'm just going to go ahead and pop the force of gravity into all these. You always get a force of gravity. All right, starting with number 7, I see a surface, so I need to draw a perpendicular force to the surface. Anytime there's a surface, I have a normal force. And I'm also going to have a tension here because it's hanging from a rope. I've got 2 perpendicular forces, so there's a normal force here, perpendicular to that surface, and a different normal force here, perpendicular to this surface. Alright, this rock is sliding down the ramp. It's kind of confusing. The word says equilibrium, the motion says acceleration, so sorry about that, I don't know what to tell you. But we do have a normal force because we're perpendicular to the surface, and we have a force of gravity. And those are going to be the only forces we have. And the only other force we could have would be friction. So if there were a frictional force, it would point that way. There is no force. The important thing is don't draw force pulling the rock down the ramp. Gravity is pulling the rock down the ramp. There's no force pointing in this direction down the ramp. There is none. All right, so for number 10, so let's just go ahead and draw in some forces of gravity here. Always a force of gravity unless in deep space, I guess. This is falling, no friction, so that's it. It's a rock falling. It's in free fall. Condition of free fall is that the force of gravity is the only force acting upon something. Having air resistance be negligible. This is a rock sliding on a table, so oh look, a normal force because we're on a table, and frictionless surface, so there's no friction.
Please come to the office. Again,
I'll pause.
Noe, Allison, please come to the office.
All right, so we have a rock falling at a constant terminal velocity, and there's a force of gravity down, and then so it's terminal velocity. That means we got dropped off a building, a really high building, so we've hit the point where we have air resistance. I'm going to call it friction, but air friction or air resistance is pushing up with the same force that the force of gravity is pulling down, and that gave us, now we have a constant speed, means our change in velocity is equal to 0, so now our acceleration is equal to 0, so now our net force is equal to 0. That is what's happening in that problem. Next set, let's throw in some forces of gravity. All right, so this is a rock sliding on the ground. Of course, there's a normal force because it's on a ramp. It says decelerating because of, so it's showing that it's slowing down. So let's go ahead and throw a friction on there because it told us to, really. And that's it. It's just the friction is slowing it down. This rock is in free fall. It's been thrown in the air, so this is all showing its path. It's falling up and going down. Well, force of gravity is the only force acting on something in free fall. And this is that same rock, and it's at the top of its trajectory. Well, guess what? Even though it's at the top of the trajectory, it still has a force of gravity pulling down on it. This is a rock that's tied to a string and it's being pulled straight up, so hey, we have a force of gravity, and we have some sort of tension, which should be much bigger than the force of gravity, or twice as big actually as the force of gravity, because it's accelerating, which means that there is a net force, which would be equal to the mass of this rock times the acceleration. Alright, so now we're dragging a couple of rocks on the ground, so we have a force of gravity in both of them. Oh, they're tied to strings, so there's a tension force in both of them. And what's different? Well, in this one, there's friction, which is causing it to go at a constant speed. It means the component of the force pulling it this way, don't draw those, is equal to the friction. This one, there is no friction, so it is just accelerating. You can see the lines getting farther and farther apart. All right, so that is a free body diagram, answer key.